Good morning, everybody, and welcome back to Abstract Algebra. All right, let's get what you all want to know out of the way first. COVID is taking off quite a bit. Plus, you're all probably frazzled and sleep deprived from, political stuff. So I'm extending the deadline for homework 65. And honestly, if you need longer, just let me know. I will be happy to extend it beyond that. Just let me know if you need a personal extension or whatever. And whatever. Because I understand this is a stressful time right now, / scary time right now for a lot of us. And now is not the sort of day that we need to have big homework sets due. So take that for what it's worth. Also, plan for the day. We're going to finish our discussion of first Isomorphism Theorem and finally move from talking about groups to talking about rings. It'll be kind of our second of the two major units of the semester. But Dr. Gerstle, what about Chapter 11? Chapter 11 was the fundamental theorem of finite Abelian groups, which we already talked about. Anywho, got my usual office hours this afternoon from 2 to 3, tomorrow morning at 10, and tomorrow afternoon at 1:30. I already mentioned homework. Any questions or comments before we get started for today? Sorry, I'm out of it too. All right. A stats professor distributes a 50-question true-false exam. Well, that sounds fun. I should do that. During the exam, the professor notices there's one student sitting in the very back of the room who's just flipping a coin over and over and writing down answers. They don't even read the problem. They just flip a coin, look at the coin, mark in true or false each time. This goes on for 2 full hours. And after all the other students have left, that one student, still back in the corner of the room, flipping coins, writing down answers. Professor goes up to the student. Listen, she says, I know you weren't prepared for the test. I know you've been flipping a coin to determine the answers. But what I don't get is, what's taking you so long? The student glares at the professor and says, shh, checking my answers. You always have the best of laughs.
Thanks.
Okay, so last time, you may recall, we proved the first isomorphism theorem, which says that if you have a group homomorphism from group G to some other group G prime, then G mod the kernel of phi is going to be isomorphic to the image of phi. Or again, the kernel of phi is just the set of things in the original group that maps to the identity element in the second group. And the image of phi is just the set of all elements in G prime that are getting mapped, that actually get mapped to from something in G.
I was supposed to remind you to give us a cool geometric description of what we just proved.
Yes, thank you. I did remember. I was going to do that. But thanks for reminding me.
You're welcome.
Useful as it was. So, we proved this last time. And what I wanted to do today is to talk just a little bit, start by talking a little bit more about this example we looked at last time, where we wanted to show that if H, look at my notes, H is a set of all complex numbers, A plus BI, satisfying square root of A squared plus B squared is equal to 1. And what I wanted to do is I wanted to show that if we took a group of all non-zero complex numbers under multiplication and mod it out by H, then that's going to be isomorphic to R plus, the group of all positive real numbers under multiplication. And the way we did that was by doing the following. We showed, first of all, we showed that the map phi is a group homomorphism. I don't know. Megan, is that what we showed first? That's what we showed first. We also showed that phi is onto, meaning that G prime is equal to the image of phi. And we also showed that the kernel of phi is equal to H. In other words, H is precisely the set of all elements that are getting mapped to the identity in R plus, or the identity element in the positive reals under multiplication is just the positive integer 1. So H is a set of stuff mapping to the identity. Phi is onto, meaning every element in our second group, R plus, is getting mapped to by something from the original group. And we also showed that phi is a group homomorphism, which by the first isomorphism theorem would tell us that if we were to take C star mod the kernel of phi, that has to be isomorphic to the image of phi. But since the kernel of phi is equal to H, and the image of phi is equal to R plus, that gives us that if we take the group of non-zero complex numbers and we mod out by H, this set of all complex numbers whose complex absolute value is 1. We take C star, mod out by H, we get a group that is isomorphic to R plus, according to the first isomorphism theorem. And we were able to prove this without ever defining a map, without ever defining an isomorphism from this group to that group. Instead, we just used the first isomorphism theorem, which required we find a homomorphism from C star to R plus, where we didn't have to mod out by anything here, that happened to be onto, so that the image of our map was equal to this whole set R plus, and whose kernel was H, the thing we wanted to mod out by. And Elaine wants me to give a cool geometric description of what does this group look like, C star mod H. So let's check out what that looks like. So it turns out you can take any complex number and graph it in a two-dimensional plane that we often call the complex plane, where if I wanted to graph, for instance, 1 plus 3i, I would just go to 1 on the real axis and 3 on the imaginary axis, and that would correspond to how you could graph 1 plus 3i. Just real component is like its x-coordinate. The imaginary part, the 3i, you could think of as being its y-coordinate, so to speak. And with this idea in mind, we could say that if we wanted to graph, say, the set H, what would the set H look like? The set of all complex numbers graphically satisfying, the set of all a plus bi satisfying square root of a squared plus b squared is equal to 1. Is this going to be the circle of radius 1 centered at the origin? In other words, the unit circle. So here's H right here. What if I graph the coset of H corresponding to 3H?
Would it just be a bigger circle?
It would just be a bigger circle. Specifically, circle 3 times farther away from the origin. And if I were to take, say, a half H, just be a smaller circle. So in other words, every coset of H in C star, which is the same as saying every element in the group C star modded out by H, is just going to be graphically represented. We can graphically represent by drawing a circle. And if we wanted to, we could multiply two circles together by just taking AH times BH is going to be equal to A times BH. So if we wanted to take the circle of radius 1/2 about the origin and multiply by the circle of radius 3 about the origin, which circle are we going to get?
Circle of radius 1.5.
Circle of radius 3 times a half, which is 1.5. So in other words, you can actually think about multiplication in this group as just being multiplication of circles, where we multiply two circles together by just kind of multiplying their radii together and taking a circle of that radius centered at the origin. So multiplying elements in C star mod H corresponds to multiplying circles. By multiplying their radii. So it's kind of cool. You could sort of, I think this is really cool. You can actually think about what does this group look like, C star mod H. You can think about it as just a group of circles where you can multiply two circles centered at the origin to give you another circle centered at the origin. The identity element is just the unit circle of radius 1, and you would multiply, and the inverse of, say, AH is A inverse H. You take the inverse of the circle by taking the circle whose radius is the reciprocal of the original circle, which I think is really cool. And what we just proved using the first isomorphism theorem is that this group of circles, where we multiply circles together to make more circles, is isomorphic, meaning mathematically the same as just a group of all positive real numbers under multiplication. Where the real what we're doing is we're associating each circle with the radius of that circle. So that multiplying the circle of radius 1/2 by the circle of radius 3 is just like multiplying the real numbers together 1/2 times 3. And our first isomorphism theorem proof here just told us that those two groups, the group of multiplying circles together and the group of multiplying positive real numbers together, mathematically they're the same. They just look a little bit different. One has a coat of fresh paint over it, but deep down they're really the same group. Any questions or comments about what we just showed? Y'all aren't appropriate. I need some oohs and ahs. You are not appropriately awed by this. This is really cool stuff. This is kind of what you get into in algebraic geometry and representation theories. You're taking these sorts of weird algebraic objects like circles, and then hey, I'm going to represent them somehow in a simpler way. We're going to take circles and just represent them by their radii, and we can talk about how multiplying circles together is really just the same deep down as multiplying those radii together. All right, let's do another one. Because you all weren't as appreciative as I wanted, this one's not going to have some cool geometry to it. Or at least we're going to talk about. I claim that if we take K to be the set of all integer multiples of the identity matrix 1, 0, 0, 1, where n is some non-zero real number. So in other words, the set of all matrices of the form n0, 0, n, then GL2R modded out by K is going to be isomorphic to SL2R. So we haven't seen these groups in a while, so let's maybe remind ourselves what it means to be elements of GL2R versus SL2R. What does it mean to have a matrix in GL2R?
Invertible?
Yeah, if A is invertible, and there's a billion different ways to say A is an invertible matrix, what has to be true about the determinant of A if A is an invertible matrix?
Equals 0.
Determinant is non-zero. Yep. Whereas A is going to be an element in SL2R. This is a group we haven't really looked at very much. It showed up in the first homework, the one where you were identifying which of these things are groups, which of these things are not groups. What had to be true about the determinant of A, if you remember, to be in SL2R?
Has to be 1.
Has to be 1. So basically, what I'm saying here is if we take the group of all 2x2 invertible matrices, meaning all 2x2 matrices whose determinant is non-zero, and if we mod out by this subgroup K of GL2R, then we get a group that's going to be isomorphic to SL2R, the group of all 2x2 matrices whose determinant is 1. So let's prove this. Okay, I don't want to have to prove this directly by defining a map from GL2R mod K to SL2R. So if we want to set this up as a first isomorphism theorem, I'm going to need a map from phi that goes from what group to what group. If we wanted to make this something where we could eventually use the first isomorphism theorem to say, aha, group mod kernel of phi is isomorphic to the image of phi, which would give us this. Phi is going to have to be a map specifically from which group to which group, in a similar way to what we did in the last problem. Right?
GL2R to SL2R.
Bingo. We're going to have to take a map, a map that goes from GL2R to SL2R. And we're going to want our map to have the same 3 properties as before. We're going to want that phi is a group homomorphism. We're going to want that phi is onto. And we also are going to want that the kernel of phi is equal to our set K. So in other words, we want to define a map phi in a way that's going to make it so that the set of all matrices that map to the identity matrix is precisely this set of matrices here, the set of all multiples, or the set of all multiples of the identity matrix. How could we take a 2x2 invertible matrix and do something to it that'll necessarily give us a matrix in SL2R in a way that'll satisfy these conditions?
Divide by the determinant.
Bingo. We're just going to take A and divide by its determinant. Which, because A is in GL2R to start with, this is an operation that makes sense because we know we're only looking at matrices which have non-zero determinants to begin with. If we allowed any 2x2 matrix, then this wouldn't work because we might be dividing by 0. Pro tip, don't ever divide by 0. Not until we get to some advanced ring theory, at least. But since we're only looking at matrices in GL2R, matrices which have non-zero determinants, this map makes sense. To be able to take any matrix and divide it, just send back A divided by the determinant of A. So basically, in other words, we're just going to take a scalar multiple of any matrix we plug in, and just take the scalar multiple where we're multiplying out in front by 1 over whatever the determinant is. So if we wanted to take phi, for instance, of 1, 2, 3, 4, that's going to be, what's the determinant of that? 4 minus 6 is negative 2. We would end up with just negative 1/2 times the same matrix, which would be, what, negative 1/2, negative 1, negative 3/2, negative 2. And that would be what we would get if we plugged this specific matrix into our map view. We get back the same matrix, but we're just dividing by whatever the determinant of that matrix is as a scalar. All right, so we have 3 properties we need to prove. Josh, where would you like to start?
It's a homomorphism.
Start with homomorphism, okay. I was very tempted to just ask you again for all 3 of them. What's that?
Somebody would not have said homomorphism.
What is it? Yeah.
Sorry, maybe I'm just making a mistake. Is that last matrix, is the determinant of that 1?
We multiply down the main diagonal, we'll get positive 1. We multiply here, we'll get plus 3 halves, negative a half, negative 1, negative 3 halves, negative 2. I don't know how to take determinants, hold on. Determinant of this matrix is 4 minus 6 is negative 2. So if we take this matrix and we divide by negative 2, we get negative a half, negative 1, negative 3 halves, negative 2, which if we take swoosh, swoosh, we'll get negative 1 half times negative 2, which is positive 1. What am I doing wrong?
Broken.
No, we're going to figure this out.
Isn't your determinant of the first one negative 1 to be? No, you're right. No, it's 6.
4
no,
minus,
yeah,
it's 1 times 4 minus 3 times 2, which is 4
you're
minus
right,
6 is
yeah,
negative
yeah.
2. You take any matrix and divide by its determinant, you should get something with determinant 1, because the determinant of this is, the determinant of that is just going to be, is 1 over determinant of A times the determinant of A, which is 1. I think I'm missing something obvious. Take a minute, talk amongst yourselves. You know what? Don't talk to each other because COVID. Take a minute, work this out for yourself, see what we're doing wrong. I'm going to think about this too, because it should be working out, and I'm not sure why, and it's freaking me out a little bit. Negative 3 halves, negative 2.
I think that's Dr. Gerstner. So if you're multiplying 1 over determinant A times determinant A,
Yeah.
determinant A is 1, right? We make that.
Well, if we're taking determinant of A divided by the determinant of A, we should get 1.
I thought I was onto something, I was not.
1 minus 2
Hey, why is this so hard? That's what happens when all the other math professors steal linear algebra and never let me teach it. I can't do basic.
That is so easy.
So we divide by determinant of that, so that is negative 1 half. 1 over negative 2 is negative 1 half.
It's absolutely
1 half, negative 1, negative 3 halves, negative 2. That is positive.
1
plus 3x equals 1. Moving on.
Oh, God, it hurts.
All right, phase group homomorphism. There shouldn't be a square root. It's just AD minus BC. These are 2 by 2 matrices. All right, phase group homomorphism. If A and B are elements in GL2R, then it should be the case that if we were to take phi of A times B, that by definition is going to give us 1 over determinant of A times 1 over determinant of B times B, which in turn should be equal to 1 over determinant of A times 1 over determinant of B times AB. Because 1 over determinant of B is just a scalar. We can just pull our scalars out in front before we do our matrix multiplication. But what's another way that we can rewrite 1 over determinant of A times 1 over determinant of B?
1 over determinant AB.
Indeed. And then 1 over determinant of AB times AB is just phi of AB by definition. So P is a group homomorphism. So next up, I'm going to decide, because I don't trust any of you all, I'm going to prove that the kernel of phi is K. So by definition, the kernel of phi is going to be the set of all A in GL2R such that phi of A is equal to the identity element in the second group. What's the identity element in SL2R?
What's the thing?
Yeah, it's going to be the same as in GL2R, just 1, 0, 0, 1. Because that's a matrix whose determinant is non-zero and whose determinant is also equal to 1. That if you multiply by any other 2 by 2 matrix, you get back what we started with. Which in turn is just going to be the set of all matrices A in GL2R, such that A divided by the determinant of A is equal to 1, 0, 0, 1. But that means if A divided by the determinant of A is 1, 0, 0, 1, that means A has to itself be a scalar multiple of 1, 0, 0, 1. Because if we take A, multiply by 1 over its determinant, that's just going to give us 1, 0, 0, 1. And what do we know about the scalar multiples 1, 0, 0, 1? That's precisely what it is. Why is that coming out and not 1? Oh, shoot. I just screwed something. Okay, I know what I screwed up. I'm not going to tell you that.
No.
I'm not going to tell you because it invalidates the entire example, and I want you to think this example works. So, last thing we need to prove is that, oh gosh, I screwed this up. What? Phi is onto. Let's see, it's going to be one of those classes. So for phi to be onto, we need to show for any element in SL2R A has to be equal to phi of B for some B in GL2R. That's what would be necessary for phi to be onto, is that given any matrix in the second group, that matrix gets mapped to by some element in the first group. So if we have a matrix in SL2R, meaning we have a matrix of determinant 1, how can we find a matrix of non-zero determinant, such that if we take that matrix of non-zero determinant and divide by its determinant, we end up with our matrix A of determinant 1.
You repeat that.
I don't see why I should need to. So here's the question. If I'm starting with a matrix A whose determinant is 1 specifically, how can I find a matrix in GL2R that will map to A? Specifically, how can I find a matrix of non-zero determinant such that when we take phi of, so call it B, how can we find some B of non-zero determinant such that when I take B divided by its own determinant, I get A? Fine?
Can't you just do A? Because then
B equals A?
Yeah.
Really?
Yeah.
Yeah. This works. Yeah, the thing that's going to map to A could just be A itself. Because if you take a matrix in SL2R, it automatically has to be a matrix in GL2R. And if we take phi of A, if we take something with determinant 1 and divide by its determinant, nothing is going to change. If we let B equals A, since if the determinant of A is equal to 1, we could just take phi of A, and we would get A divided by its own determinant, which is just going to give us back A. Nito, Dor, Rito. We've shown that phi is a group homomorphism. We've shown that phi has a kernel of K, meaning K is precisely the set of elements that map to the identity in GL2R. We've also shown that phi is onto. Thus, we can say, by the first isomorphism theorem, we know GL2R modded out by the kernel of phi has to be isomorphic to the image of phi. But since kernel of phi is equal to k, that's saying that GL2R modded out by k has to be isomorphic to the image of phi. And since phi is onto, we know exactly what the image of phi should be. It's just going to be all of SL2R. And that's how first isomorphism theorems typically, proofs typically go. You could probably expect 1 or 2 questions like this when you all are taking your second exam next week. Oh wait, did I just? By the way, we have reached the end of group theory just about. And that means it's exam 2 time. Dr. Bursey, you haven't finished grading exam 1. I am painfully aware of this. I've worked on exam 1 grading, actually about halfway done. I'm going to try and finish exam 1 grading by Friday. If not Friday, definitely this weekend. So that you will have that to look off of by the time exam 2 happens. But you can probably expect exam 2 will be like exam 1 and that it'll be, it'll be take home. You'll have a week to work on it. You are allowed to work with up to 1 partner. But, socially distanced. And virtual / wearing a mask, please. The outbreak's already going on. I haven't officially announced that yet, but that's kind of my current thoughts is I'll give the exam like next Wednesday and you'll have like a week to work on it. And then I'll probably extend the deadline because everyone's stressed out and or sick and or in quarantine. Any questions about what we just showed? This is what your typical first isomorphism theorem proof is going to look like. Is you want to show a quotient group is isomorphic to some other group. You find a homomorphism from the group you're quotienting out by to this other group. You show it's a group homomorphism. You prove its kernel is the thing you're modding out by. And then you prove that your homomorphism is onto, which tells you that the image of your homomorphism is equal to this other group. And once you've done all these things, then the first isomorphism theorem will tell you your original quotient group has to be isomorphic to the other group you're looking at. And life is hunky-dory. Any questions or comments? Yeah, so?
You know what the mistake was?
No. This doesn't have to have a determinant of 1. I think that is what I screwed up. I think I'm using the fact that like if you take the determinant of A divided by the determinant of A, you can't pull scalars out in front of determinants because technically you need to do that k times, where k is the number of rows in your matrix. So this is not actually a function. But if it was, this would be a cool example, and I just realized that just now, and I apologize for giving you a non-example. I promise not to do that on the exam.
A counterexample that worked.
I mean, this all checks out other than the fact that it's just not something that ends in the group you claim it is. All right, this is what happens when I don't get to choose my answer. All right, I want to prove one more theorem, and this is kind of a fun theorem. It's the theorem of canceling out fractions, where your fractions happen to be quotient groups. You flip to the back page On the back page, I listed a few kind of corollaries to the first isomorphism theorem. And I want to prove the fourth one of these. So the one I want to prove is, I already mentioned this, number 4, which is, I'm going to list as a corollary and say that if H is a normal subgroup of G and K is a normal subgroup of H, then I claim that if we were to take G mod H, that's going to be isomorphic to the group G mod K mod H mod K. G mod H is isomorphic to G mod K mod H mod K. Which I think is kind of cool because if you were to think about these as being like fractions and take A divided by B divided by C divided by D, you're just going to get A over B divided by, let's say, C over the same B. That would, as fractions, normally give you A over B times B over C, which would be your A over C, which is exactly the same sort of thing we're ending up here, where we get a G mod H. So this corollary has a name. Would anybody like to guess the name of it, considering it is the fourth item on corollary of the first isomorphism theorem? I want to make a guess as to what the name of this theorem is.
The fourth corollary of the first isomorphism theorem.
Nope. It is the third isomorphism theorem.
So that just doesn't make any sense.
It's delightful, doesn't it? I'm not even going to tell you what the second one is because I don't like it.
Oh.
So here, we're going to prove the third isomorphism theorem by finding a map from G mod K to G mod H. And what our map is going to be from G mod K to G mod H. And the way we're going to define this map is we're going to take a coset of K, little g K, and what would be a nice way, if we're taking some little g times K, what do you think would be a way that we could take that and spit out a coset of H instead of a coset of K? Any ideas for some way that we could take this coset of K in particular and somehow spit out a coset of H? Perhaps involving the same little g somehow? Right?
You do B of G little k, or just G little k where k is a member of H.
Close. Not quite. We need to map to an entire set of elements, keep in mind, an entire coset. We're just going to map it to the same little g times H this time. And I claim this is going to give us an onto group homomorphism whose kernel is equal to H mod K. So before we start proving anything about homomorphism and and onto and that the kernel is what we want, there's something else we need to do first. We need to show that phi is a well-defined map. Anytime you're defining a function whose inputs are cosets, not just single elements, but entire sets of elements, you always need to check that your map is well-defined. Meaning, you need to check if we have two cosets that are equal but look a little bit different. If little a sub k equals little b sub k, we have to check, must it be the case that phi of the first coset equals phi of the second coset? Because that's oftentimes not obvious if you're looking at a function that takes in cosets as its inputs. Is if you represent the same coset in two different ways, will it necessarily give the same output when you plug it into your function? So let's check. If we were to take, we could say that if AK equals BK, then I claim that's going to tell us that A times B inverse K is equal to K, which is the same as saying little ab inverse has to be an element in K. From the fact that A and B generate the same coset in K, that's, if we take little a b inverse K, that's going to give us K. Well, the only way that that happens, we have a theorem in our cosets worksheet that tells us if we take an element times K and get back the same coset K, that means that the element has to itself be an element in K. Well, we can say since AB inverse is an element in K, and K is a normal subgroup of H, what else does AB inverse have to be an element of? It's an element in K, and K is a subgroup, a normal subgroup of H. Where else can we claim that this element little a b inverse has to live?
In H.
Yeah, has to live in H. Because part of being a normal subgroup is being a subgroup, which means if K is a subgroup of H, then every element in K has to also be an element in H. So we know AB inverse is an element in H. And then from there, we're basically making the same argument backwards. We can say then AB inverse H is equal to H. And so AH is in fact equal to BH. I.e., phi of AK is going to be equal to phi of BK. So we don't have to worry about our map not being well defined. Even if you take the same coset and represent it in two different ways, no matter how you represent your coset, whether it's with an A or a B or with anything else, if you were to plug that coset into the function phi, you'll always come out to the same thing, the same coset of H in this case.
Is this argument work if K is not a normal subgroup or just a regular subgroup?
This will, excuse me, if K is just a normal subgroup of H, this works. The reason why we needed normal subgroup is if we didn't have a normal subgroup, these would not be, specifically this would not itself be a group. And we need this to be a group so we can modify it. H mod K is only is a subgroup, remember, or is a group if and only if K is a normal subgroup of H. And ditto with H being a normal subgroup of S. So there's that. We've proved phi is a well-defined map. We need to prove our three other things. So I'm guessing, Megan, I want to go show that phi is a homomorphism next. So to prove that, I'm going to elect AK and BK, the elements in G mod K. And if that's the case, then we can say that if we were to take phi of AK times BK, well, which coset of K would we get if we took little a times K and multiplied that by little b times K? What coset of K would that end up giving us? Right?
ABK.
Little ab times K. Which, phi of that, by definition, is just going to be little ab times h, which is going to be just phi of, or not phi of anything, it's going to be little ah times little bh, which in turn would give us the same thing as phi of ak times phi of bk. So if we multiply our cosets together and then apply the map phi, we're going to get the same thing as if we apply phi to each coset and then multiply the corresponding results that we would get together. So phi is in fact a group homomorphism. So next up, I'm going to prove that the kernel of phi is going to be what? H mod k. That's going to come about because we can say that the kernel of phi is, by definition, going to be the set of all elements in our, what are the colon and not an equals? The kernel of phi is going to be the set of all elements in G mod K such that phi of AK is going to be equal to the identity element in G mod in G mod H. What is the identity element in G mod H? We want to find the set of things mapping to the identity element in, this is, oh my gosh, not G mod H, in G mod, no, yeah, G mod H. I'm sorry, it's hard, I'm out of it too. That's not abundantly clear. We need the identity element in this quotient group in order to be able to say what is the kernel of our map phi. So I'm just going to tell you, because I don't think any of us are up to really thinking too hard right now. The identity element in G mod H is just going to be H itself. So in other words, we want to find all the cosets A sub k such that if we took phi of A sub k, we're going to get H. So in other words, it's the set of all cosets of k in G, so the elements in G mod k, such that if we took A sub H, we're going to get back H. And what do we know has to be true about A if we're saying that little a times the subgroup, or times the coset H, gives us just H itself back? What has to be true about A to make this equation, in other words, work out? Okay? A doesn't have to itself be any sort of identity element necessarily in order for AH to be equal to H. It could be, and that would certainly be one way of, if A is the identity element, then this would certainly be true. But A could also be some other things that would also make it true.
It has to be a member of H?
A has to be an element in H itself. And so, what can we say about all the cosets in G mod K such that A itself is coming from an element in H? Well, that's just going to be H mod K. The set of all cosets of K represented by an element in H. Because both of these are going to be equal to the set of all elements of the form little hk, where H is some element coming from H. So the kernel is in fact H mod K. And the last thing we need is that phi is onto, which means given anything in our second group, we need to prove it's equal to phi of something in our first group. So we need that for any element, I'll call it A sub H in G mod H, AH is equal to phi of BK for some element BK, an element in G mod K. And how can we specifically choose a B such that if we took B sub K and took phi of that, which keep in mind, phi of BK is just going to be BH by definition. How can we choose a B such that phi of BK will have to give us back AH specifically? So what would be our way of choosing a B such that BH would give us the same coset as AH, in other words? Yeah, let's pick B equals A again. We can do this, that if B is just equal to A, then phi of AK will give us AH, and that checks out. We've shown that given any element in G mod H, we can find something in G mod K that maps to it. Just take the exact same coset where you've replaced H with K again. And now that we have all that, we can say thus, By the first isomorphism theorem, we know that G mod K mod the kernel of phi is going to be isomorphic to the image of phi which, since we know that the kernel of phi is h mod k, is going to tell us that G mod k mod h mod k is isomorphic to the image of phi. And then since phi is on 2, we know that the image of phi is just going to be precisely G mod h. Are you all sick of quotient groups at this point? We're going to take a break in the next packet from them. But don't worry, they'll come back. They always do. So it's going to do it for today. Hold on to those ring theory packets because we are going to be starting in on ring theory in class on Friday. So hope you all have a good rest of your day. I'll talk to you all on Friday. Don't forget, homework 6 not due tonight anymore.